Good afternoon, everybody. Thank you for joining for this Elastic MapReduce deep dive, best practices, tips and tricks session. I'm Ian Myers. I'm a solution architect based in the United Kingdom, and I work with customers around Europe building systems on top of Elastic MapReduce, on top of Redshift, Kinesis, DynamoDB, and it's a fantastic ecosystem. And hopefully we'll reward your perseverance for coming to the last session of the day with some interesting stuff that you can take home and make your Hadoop systems run even better. To start with, it's worth recapping what Elastic MapReduce is and what people use it for. So it is a managed Hadoop environment where we take responsibility for standing up the infrastructure, installing Hadoop, and giving it a high-performance network on which we then can run Hadoop 1, Hadoop 2, and tools that are built to run on top of the Hadoop ecosystem, including tools like Spark and Shark, Presto, and we'll talk in some detail about how you can build extensions on top of Elastic MapReduce that make Elastic MapReduce really an unlimitedly powerful parallel processing container. It's designed to integrate with S3, DynamoDB, Redshift, and Kinesis natively. And then, of course, with tools like SQL connectors, you can connect to any type of data source on premises or to import third-party data feeds. You also have native support within Elastic MapReduce for spot instances. Elastic MapReduce gives you the ability to say, I want X number of machines, and I'm willing to pay a certain amount for them. And Elastic MapReduce will provision those machines and introduce them into your cluster automatically. You don't have to worry about provisioning them and managing the spot price over time. We can also run things like HBase on top of Elastic MapReduce. So you can have an ultra-high performance key value data store where you don't have to worry about the cluster topology. And we'll talk about some of the tools that can be built on top of that. At its heart, Elastic MapReduce is a service that controls the infrastructure by provisioning EC2 instances in a set of instance groups. There are 3 available instance groups today. The master group contains the name node for Hadoop. And then we can provision a core instance group, which is responsible for storing data in HDFS. Runs the data node as well as task tracker and job tracker processes. We can also provision what's called a task group. And a task group provides task tracker and job tracker processes, but it doesn't store data. It's designed to use the core nodes as an HDFS file system, while also being able to take advantage of ultra-performant access to S3, and all of the instance groups run an optimized access path to S3. So you're able to be extremely flexible about how you build your cluster. Your master group might be one instance type, and your core nodes might be a completely different instance type. The task nodes as well, because they're not storing data, you may have no requirement for local disk on those machines. You may just be provisioning machines that are particularly high on RAM or high on relative amount of CPU. So in a lot of ways, Elastic MapReduce is like every other Hadoop that you will use on premises or built on top of EC2. You can run a variety of distributions. The default is an open source-based Apache Hadoop. And you can also run 3 different versions of MapR's Hadoop. M3 is a fairly standard Hadoop environment with some unique extensions from MapR, for instance, the ability to mount the HDFS file system as NFS. And then you can also run M5, which gives you a name nodeless architecture, meaning it's very highly available, or MapR M7, which is designed for very high performance, pauseless garbage collection in particular for running HBase. We give you total access to the Hadoop configuration, and we give you root access to the machines. In no way would you consider Elastic MapReduce a black box. You have as much control over this environment as you do the cluster that you would build yourself on top of EC2, but you're able to take advantage of all of the installation automation in order to make your job a lot easier, so that you can focus on what is the logic that I'm deploying, what is the business problem that I'm solving, and not doing the undifferentiated heavy lifting of installing software, managing upgrades, and ensuring that tools work together between different versions. You can install absolutely anything you want on the cluster. As part of your workflow, you can completely reconfigure Hadoop and bounce the nodes if you need to. And we've done all of the hard work for a given configuration of Elastic MapReduce to ensure that the tools that we help you install will work nicely together. So instead of you having to worry about, will this version of Hive be able to talk to this version of HBase, we've done the tweaking to make sure that those will play nicely together. But that said, you always have the ability to upgrade those tools at any time. So let's talk about configuration for a minute, because it's an important part of what you may do as you move deeper and deeper into your delivery of software through Elastic MapReduce. And it's important to know what's there that you may want to change from a configuration perspective. The first thing we might want to do is change the core Hadoop configuration. This is done through a bootstrap action, which is software that's run on the cluster on startup or on resize. There's a particular bootstrap action called configure Hadoop. And you can supply it arguments like a keyword plus -config file or key value pairs that allow you to override any parameter in the Hadoop system overall. If you want to completely provide a Hadoop configuration off of your existing on-premises environment, you can just supply that existing core side XML, HDFS side XML. Or you could just take the things that you've changed within those configuration files, and when you supply us with that file, we will just merge it on top of the Hadoop configuration that's deployed to Elastic MapReduce. Equally, individual key and value items can be used to override specific properties. We also have these little useful macros. So instead of having to indicate core-site.xml or mapred site, you can just say mapred, or you could just use the character M, and it makes your configuration changes very terse when you want to deploy them. So what would be an example of how we would use this? Well, as we'll review a little bit later, we configure the capacity of each of the instance types based upon our experience of what makes it most stable and the best performance per dollar. And an example of that in Hadoop 1 is that we'll set the number of task tracker nodes that can be run, or task tracker processes that will be run on a given machine. And that's based upon its instance type and family. You might use the configure Hadoop action to supply an override for the mapred file, supply a new config file, and then set the number of maximum tasks for mapping to 2, which might be so that you can increase the number of tasks you have for reducers. You also might increase the number of map tasks that you can run on a given node if you know that your mappers don't use a lot of memory. It means you just get more throughput out of each individual machine. Another option, if you had the need to generate fairly small files and you wanted to iteratively process those on HDFS, you might lower the HDFS block size from the default of 128 meg to 1 meg using a command such as that. So there's a lot of ability to configure the internals of how Hadoop is working. And we can also do things, particularly in Hadoop 1, such as forcing Hadoop to reuse map task JVMs. This is really important because a mapper, from the perspective of the operating system, can take between 2 and 20 seconds to start up, depending upon what you're asking from a configuration perspective. So if you set MapRed job reuse JVM num tasks to -1, we will start up one map task, one mapper process, and then it will be reused, which means we avoid that processing overhead. And if you want to use this with your own software, you're very welcome to do so, but keep in mind it effectively makes your map processes stateful for the entire time they run. So if you're coding in Java, you need to think about the impact of that. So this is a great example of a way that you can immediately get better performance from Hadoop 1 simply by setting JVM reuse. But what about the JVM itself? What if we didn't just want to override the configuration of Hadoop, but we wanted to deeply change the configuration of what the operating system sees? We would do this, for example, because you find that the nature of your task requires different settings, particularly for something like the fixed heap size or garbage collection. You can use the configure daemons bootstrap action to change the properties of JVM. The question is, which JVM? You supply the name of the JVM that you want to configure, and they vary between Hadoop 1 and Hadoop 2. And then you can supply options that you would typically supply when you do the run Hadoop command. And here you can see that we're setting the GC time ratio to 19, and we're increasing or decreasing the heap size for example, the name node to 2 gig. So this allows you very, very fine-grained control over what it is that's being run. But crucially, these are overrides to configuration that you supply when you define the cluster. It's a one-time thing, and then we apply it across the entire cluster for you. There's no requirement for you to go and visit every node, which of course would be impossible when we look at customers running 500, 800, 5,000 nodes a night. So that's how it's like everything else that you will have used on-prem or on EC2. Let's talk about what's unique about Elastic MapReduce and things that you can use that will really allow you to differentiate your Hadoop processing. Things like EMR consistent view, taking advantage of sophisticated bootstrapping, or taking advantage of a very unique feature, being able to resize the cluster dynamically. And then also, crucially, keeping in mind that we can use any type of instance that's supported by EMR within the cluster. And of course, you can change it over time. And it's absolutely appropriate that in some cases, as your workload grows, either seasonally or from month to month, you may want to change the node type for each of those specific instance groups. So EMR consistent view is a new feature that was released a few months ago. And it gives Elastic MapReduce the ability to have a consistent and always up-to-date view of data on S3, even when working on storage systems like US standard for S3 that has eventual consistency. What it does is it ensures that all of the files that are generated as output as part of a Hadoop job are available through the step API, and there's no chance that a file that's generated within one step won't be available as subsequent input to other processing steps. You can use a command line tool to import data and synchronize data between HDFS and S3 and the EMRFS system. What EMRFS is under the hood is essentially a set of indexes that are maintained on DynamoDB that allow us to track the fidelity of job output over time and also give us a massive performance boost when listing files in particular. So if you have jobs today that have a very large number of small input files, EMRFS may give you a significant bump in the performance because we spend very low amount of time doing a list against S3. We instead use the EMRFS metastore. That metastore sits on DynamoDB. You can configure it however you want. And crucially, as we saw in the last session, we can change the read and write IOPS that we provide to that metastore through DynamoDB directly. And again, with our configuration options, we can override the features of EMRFS using the EMRFS site XML or the FSS3 consistent system properties. EMR consistent view is also provided absolutely free of charge on top of Elastic MapReduce. So please turn it on. An example of using the EMRFS command line tool would be to synchronize data between your EMRFS index and a specific bucket. So for those of you who'd be interested in taking your existing workflows and turning on EMR consistent view, you simply need to do a sync with the bucket and the metastore that you've created through EMRFS. And again, you can see some of the commands that you would use for describing that metastore, setting its capacity, cleaning it up. Of course, you can delete entries from the metastore if you want to, but of course, we would encourage you to keep your metastore as up-to-date as possible, and then you can just do a blanket import with the EMRFS tool. So let's talk about what those files should be that sit within EMRFS on S3 or on HDFS. It's a very simple best practice I'll give you. Avoid small files, pretty much at any cost. And small for us is defined as anything sort of smaller than 100 meg. The reason for that, as we talked very briefly about, is that mappers and reducers take time to start up. And Hadoop will generate those tasks in Hadoop 1 or Hadoop 2 based upon the number of input files or input file splits. So the more files we have as input to a job, the more time we spend spawning tasks and not doing useful work, which means our cluster runs longer, we spend more money. And so, sorry, my clicker is, there we go. So an example would be if we had 10 terabytes of data and we had 100 meg files, we would be generating potentially 100,000 mappers. And best case, 2 seconds per mapper spawn gives us a total time of 55 hours just to spawn the task. That's not doing any useful work for you. But if we compare that with gig files, we reduce that time exactly linearly. We reduce the number of tasks that we need to spawn in order to process that data, which means we spend significantly more time actually working with the file contents rather than starting up, shutting down, starting up, and shutting down. So what's the best file size? We generally recommend 1 to 2 gig, if possible. Why is that? Well, an individual task in Hadoop, we don't want to have running for an overly short period of time. 60 seconds is a great rule of thumb. If we're constantly starting up and shutting them down, we're spending a lot of time in the operating system and not working with data. So if we set 60 seconds as the amount of time we want to be working with our data, then we see that an individual task is probably going to get 10 to 15 megasecond to S3. And based upon the instance type in the core group, you'd have to measure the I/O rates to HDFS. But if we look at that then speed, 15 meg times 60 seconds gives us around a gig. That can be pre or post compression, certainly up to you, but very useful rule of thumb. And for any of you who have very, very small files sitting on S3 or even on HDFS, you can get an immediate performance boost just by aggregating those files. So what do you do about it? Well, if you do have lots of small files, there is a utility provided with Elastic MapReduce, which is an extension of the distcp program called S3 distcp. And S3 distcp is designed to give you a very high performance way of working with data on HDFS or S3. Particularly, it allows you to move data between S3 and HDFS, but also do interesting transformations. One example that we see, and we absolutely encourage you to use, is the ability to aggregate small files together on the basis of a pattern that you apply to your data. And you have the ability to set a target size for the data of whatever you require and whatever is appropriate for the layout of data on S3 or HDFS. You can see the example using the EMR command line to add a step to a running cluster that will aggregate our files. In this case, we're saying that the files live on S3, my AWS bucket/CF, and our destination is set to be HDFS. So in this case, what we'd be doing is taking a large number of small files up off of S3 and putting them into HDFS, but aggregating them at the same time by applying a group by, in this case saying, I want to group everything by instance ID. For example, if we had application log files and we're setting a target size of 128 meg, for example. So a very simple command that you can run on your cluster, and it will immediately give you performance benefits if you have lots of small files. And the number of customers we see with 100K, 200K files is significant, and this is a great way to get better performance. We also encourage you to use compression along with thinking about the size of the files that you store on S3 or HDFS. Again, a very simple axiom. Always, always, always compress files. We absolutely appreciate that sometimes you're being delivered a feed of data that isn't compressed, and that's fine. But we absolutely should apply compression wherever possible. Whether it's the intermediate data that's generated on HDFS as the output from map processes, or when we write data back down to the system of record, whether that's HDFS or S3, we should absolutely compress that data. The reason is we will get much better performance because we're going to do a lot less I/O. We need a lot less bandwidth between Elastic MapReduce and S3. And ultimately, it will save you money on S3, which is fairly obvious. So what type of compression to use is often a question. And it's important to keep in mind that Hadoop offers many different types of compression. Some of them are really fast, but they're not that space efficient. Others are extremely space efficient, but they're extremely slow. And then also evaluate your compression choice on the basis of whether or not it's splittable. The default that most people will settle on is gzip. Unfortunately, gzip's not a great choice because it's a file-level cipher. It will only be able to tell a process that's trying to decompress it what is being decompressed when it reaches the end of the file. So if I have a 1 gig file, everybody who wants to read that has to get the whole 1 gig before they can start decompressing. A splittable compression codec has internal markers that tell a reader process that it has reached a milestone and that that data is internally consistent and can be decompressed. Streaming codecs are much, much faster on Hadoop, and we highly encourage you to use them, especially when you get into much larger files. You can see an example there on the table of some of the comparisons that we've observed of the space efficiency of a given codec versus the encoding speed. gzip is extremely efficient at compressing data, but unfortunately, it's also extremely slow. And it's a file-level protocol. If we look at Snappy, which was designed from the ground up for speed, we can see it's extremely fast at encoding and particularly decoding, but we don't get as good a compression rate. But when I look at this table, I always think, well, the difference is about 10% versus the performance impact being 25 to 30x. So a little table that you might use to decide, and of course you can use all of these different types of compression, is if you have a latency-sensitive job, if you need extremely fast compression and decompression, then of course you want to choose a codec which will give you those attributes. That said, if you have lots and lots of data, petabytes of data, that 10% compression overhead might actually cost you quite a lot of money. And it's appropriate in some cases to use a much more space-efficient compression codec when you have lots of data, or particularly if it's cold data that you don't look at very often. And lastly, my personal advice to you would be that if you don't have any particular requirement, use LZO. It's fairly space efficient, it's extremely fast, and it has support across Hadoop 1 and Hadoop 2. And there's a large variety of command line tools on Windows, Mac, and Linux to be able to work with that data. So it's a very good choice. And if you ever want to change it, one of the other nice features of S3 DistCP is that you can just supply an output codec. So you might have an S3 DistCP job that didn't do any aggregation. It's always good to do so, but it doesn't have to. It might just decompress the contents and then recompress them as a different compression codec. So with one fell swoop, you all can go back to your Hadoop environments and your S3 environments, run a single command on an Elastic MapReduce cluster, and you can apply a streaming compression codec and aggregate your data into a new layout that could give you massive performance improvements. And it's really worthwhile to spend a little bit of time engineering the layout of the data on S3 for efficiency. But where should this data be? Let's talk about S3 and HDFS and the relationship they have with each other. We really encourage you to use S3 as your primary and permanent data store. The reasons are myriad. It has a design for 11 nines of durability. It gives you features like server-side encryption, the ability to turn on versioning so you can protect yourself from data corruption. And you can also apply automatic lifecycle policies to archive old data down to Glacier, for example. And of course, we're going to use the HDFS file system for the intermediate storage on a cluster. And this is operationally really, really simple. Because we run our cluster, we have input data on S3, output data on S3, and there's no sort of additional steps necessary to prepare our cluster for processing. It also gives us probably one of the most important features that you can take advantage of to save cost. And that's the ability to shut your cluster down. Many of the Hadoop clusters that we see customers running will be run periodically, whether that's every day, every week, or even every 4 hours to process data. You certainly will have clusters that are always on, which we'll talk about a pattern for. But the fact that we can shut down the cluster can reduce our costs so significantly. Some customers see up to a 70% cost reduction in their overall Hadoop spend, that they can do something even better. They can make their clusters bigger because they're not running them for as long. They maybe then save 30 or 40%, but all their jobs get done twice as fast. Fantastic outcome. When you use S3 as your primary store, you also don't need to think about scalability of HDFS, nor do you have to think about the replication that's going on the Hadoop cluster, because S3 is handling that all for you. Also, S3 is designed to scale with your data. As you do more and more reads against S3 data, it will internally scale up to meet that demand. And of course, it's a virtually unlimited storage platform. Your HDFS environment within a cluster will not be. And in some cases, customers will have to change the size of their jobs over time to deal with the fact that the HDFS requirements change significantly. And using S3 as your primary store means that you can avoid that sort of optimization. The other thing it allows you to do is share data between heterogeneous clusters. Some of you may be running Hadoop a bit like a monolithic piece of kit that you have to install and babysit to keep online. But this idea of being able to shut down our cluster, save money, also can then be applied to the fact that we don't have to just run one cluster. We might run lots of clusters, each with different characteristics that are adapted to this type of processing we're doing. We might have one HDFS cluster that's backed by SSD, so we get ultra-fast and low-latency access to HDFS. We might have another one built on top of HS1, so we can take advantage of 48 terabyte local storage. And doing this sort of topology with HDFS can be done, but it's fairly complicated to ensure that your clusters talk to each other, particularly if you're using transient clusters where things like the cluster name will be changing all the time. And we really encourage you to take advantage of the S3 features that are provided at no charge, server-side encryption. Lifecycle policies just mean that you don't have to do any sort of explicit conversion to Glacier storage. Your data is just moved for you. And it also allows us to build these really elastic clusters. We're able to add and remove nodes from our cluster dynamically, knowing that the data is stored on S3. We're not going to have an impact of that resize operation, which we're going to talk about shortly. But you say, what about data locality? Surely the whole point of Hadoop and the MapReduce architecture is that we're sending compute to data. Now, it is very important that you run your cluster in the same region as your data. Hadoop absolutely can pull data across the Atlantic or all the way around the globe if you want it to. But of course, it will incur a latency penalty when it does that, and that will directly impact the performance of your job. It's often much better to move data once with S3 disk-CP between regions, and then process it in the region where that data lives. And no amount of high speed and optimized I/O access to S3 is going to make up for the fact that we're calling data that lives in Singapore from US East, for example. And the thing to keep in mind is that if your jobs are particularly memory or CPU heavy, data locality is not actually doing that much for you. Once you've got a chunk of data, you're going to work against that. And the amount of time that we need to spend, this 60-second rule, will massively outweigh the data transfer time. So we really can just focus on that. But there is, of course, an exception to every rule, which is, what if your job isn't CPU or memory bound? What if it's I/O bound? And we do encourage customers to use their local HDFS, particularly for jobs which require repeated access to data. An example of this would be if you had a Hive job where you imported some data off of S3, and then you ran a bunch of transformations against that one core set of events into different types of aggregations, for example, then you would get a lot better performance by first lifting that data up into an internal table in Hive so that we're only using the local access. But that doesn't change the fact that we want to use S3 as our permanent system of record, especially so that we get 11 nines of durability of that data. So the pattern that we would use then is that our data lives long-term on S3, and we launch our cluster and we copy the data up using S3 diskcp onto the HDFS file system. Process it in place, and at some point, certainly before we shut the cluster down, we send a backup of that data back to S3. Gives us a lot of really nice advantages, particularly for I/O-intensive workloads. But again, we get the system of record on S3, so we kind of get the best of both worlds at the cost of increased operational complexity. You have to administer the fact that your cluster is lifting up a data set into HDFS before it does work, and you have to ensure that that data is stored back down to S3 for long-term storage. But in many cases, this can be very, very useful and allows you then to optimize your cluster for HDFS access. So what's an example of where we might see this in use? If we had an application which was taking advantage of Kinesis for streaming data, we'd see that data being pushed into a Kinesis stream, which we can scale up and down dynamically. And we might have a set of Kinesis-enabled applications, one of which was using the Kinesis connector library for S3 to archive that data long-term to S3. That is a best practice of mine for Kinesis. Always store your raw events on S3 in a compressed format so that you can reconstitute the stream at some point in the future. But we'd have another Kinesis-enabled application running on the same machine, running on a different one, doesn't matter. And it might be loading an HDFS cluster in real time. For example, if we wanted to do real-time processing with Spark. We apply maybe a Spark ML model on top of that data that we've loaded in near real time into our HDFS system. And then we take the output of those models and we push it down to S3 as an aggregate set to be consumed elsewhere. And then we might take advantage of the fact that Redshift can be loaded from Elastic MapReduce directly from HDFS using the copy command. And so we've got a real-time processing pipeline that's taking advantage of this high-performance HDFS file system, in-memory processing with Spark, and then pushing the aggregate results out for subsequent reporting. So how would we do this? How would we extend Elastic MapReduce to do this kind of processing? Again, Bootstrap actions give us the ability. We touched briefly on configure Hadoop and configure daemons that configure the internals of Hadoop or the JVM. But there are also Bootstrap actions to install, of course, Hive, Pig, Impala. But there are newer Bootstrap actions that will allow us to install Apache Phoenix on top of HBase, which is a SQL library for working with key value data stored in HBase. Spark and Shark, of course. And then support for tools like Presto, which is a non-MapReduce-based SQL engine on top of file data. And for those of you who are interested in learning more, particularly about Spark and Shark, Spark SQL, and Presto, there's a session tomorrow morning at 9 o'clock called Running Your Data Warehouse on EMR. So I'd encourage you to go to that one. We also have this concept of tooling macros, which are sort of wrappers around Bootstrap actions, where we've taken all of the responsibility for building that Bootstrap action and turning it into something useful. To run Hive, you get Hive 13 now, for instance, with support for ORC files. ORC files are a columnar file format, particularly designed for large amounts of low cardinality data. We also have access to window functions, like you would see on Amazon Redshift or extremely powerful MPP platform. With Pig 12, we get streaming UDFs that you can write in Python. You get native support for Avro and Parquet. You can run Impala with the ---- Impala interactive macro that gives us in-memory SQL processing, support for Parquet, all of the stuff that you would expect from Impala. And then, of course, HBase is just --HBase or a tick box on the AWS Web Console. And we get HBase 9418 is the latest version, which gives us read replicas and read caching, transaction support, and database snapshotting. Really useful features. EMR is also integrated directly with Kinesis. We can read data directly from a Kinesis stream into Hive, Pig, streaming, cascading, with no intermediate data storage. There's no S3 and no HDFS involved. And it's a very, very simple and nice way to introduce streaming data into what is formerly a batch-based system. It means you can move from file-based transport to stream-based transport without having to change your Hadoop jobs. And then in time, you may rewrite those Hadoop jobs as Spark streaming, Kinesis-enabled applications, or something else. An example of that in Hive, for example, if we had a telecoms application, we might have some call data records that we want to track. We say that those are CSV data, in this case a comma, and we indicate that they're stored using a Hive Kinesis storage handler. We indicate the stream in the table properties, and then we can just run select statements, HQL statements, on top of our Kinesis data. All of the data serialization is handled for you. There's no intermediate data storage. And it's a very nice way to take a raw input feed and micro-batch process that, maybe just storing it back onto S3 as aggregated files. We also just announced support for Hue. You can now run the Hue user interface for Hadoop, which gives you a web-based GUI for working with Hadoop. Gives you things like an S3 and an HDFS browser. For example, you could give your end users the ability to upload CSV data directly through a web application and into your S3 buckets. We get Hive, Pig, and Impala query editors that do syntax checking, validation, and then when you run them, it does all of the process tracking and gives us access to the allocation of containers or tasks to individual nodes, and we can see a monitoring interface. It also has support for LDAP authentication, so your end users can be authenticated straight into Hue through Active Directory or Samba. That's a snapshot of what it looks like. It's a very nice tool, and will give you a much better experience for those customers that you want to expose your raw Hadoop processing to. You can also create brand new Bootstrap actions if you want to. They're just bash scripts by default, and they run as root. And you can do absolutely anything in them, anything. They run on cluster startup or cluster resize, and one little tip for you is when you run an EMR cluster, in the console or the job description, it will tell you which AMI it's running. If you want to build new Bootstrap actions, you can run that AMI as a T2 micro, for example, do all of your development there, and then know that it will be compatible with the operating system that Hadoop will be running on. We also maintain a GitHub of Bootstrap actions that you can clone and extend for things like Accumulo. Phoenix is in there. Node.js support is in there. Lots of very useful Bootstrap actions. So we'd encourage you to have a look at the Amazon EMR repository, Bootstrap actions. So now we need to very quickly talk about sizing our cluster. It's important to understand the difference between Hadoop 1, where we have static numbers of tasks allocated per node type, and Hadoop 2, where we have a much more variable allocation of tasks to the containers. And what we're going to use from a sizing perspective as we look at this, and an axiom that you might choose to follow, is that there is a setting on Hadoop 2 called container max RAM. And if you have jobs that are memory bound, then we can work out how many tasks we will typically run by dividing the container max RAM by the MapReduce RAM. And this is all documented in the Hadoop 2 AMI reference. And this is a very useful thing to keep in mind when we size our cluster, because the capacity of Hadoop is not based upon machines. It's based upon tasks. And this shows you a table of how the number of map or reduce tasks in Hadoop 1 will map onto the different instance types, as well as things like CPU capacity and storage. So our suggestion to you is use M1 and C1 for functional testing because they're cheap, and you're not going to run them that long, but certainly use M3 and C3 for production. You definitely want to use CC2, C3, and in future C4 instance types for very memory and CPU intensive jobs, but also take advantage of the storage optimized instances like HS1 with 48 terabytes of local storage, High1 with 2 terabytes of SSD, that will do about 120,000 IOPS each, or I2. And also generally we encourage you to run a smaller number of large nodes than always scaling horizontally. The reason for that will become clear in just one moment. So an observation for you that we've taken is that M1 and C1 is very heavily used across Elastic MapReduce. But on those clusters, the HDFS utilization tends to be extremely low. And in that case, it is much better for you to use M3, C3, because we get a better performance per task per dollar from the C3 and M3 families. For example, here, the cost on an M3 extra large is half of what you're getting on an M1 large, similarly sized instances, but it's even more pronounced on the C3. For the right instance type, we're getting 7x cheaper performance per task. So we highly, highly encourage you to migrate your M1 and C1 workloads over to M3 and C3. So how many nodes do you need? Well, there's a simple cluster sizing calculation that we can use. You figure out how many tasks your job is going to use, and you can either guess or you can measure that empirically. And then you pick an instance and note down the number of tasks. This is in the task configuration documentation. Sorry. We need to pick some sample data files that we want to run against, and we'll run a cluster with a single core node to process this data and note down how long it takes. And then there's a formula. The number of nodes is the total tasks times the time to process these sample files divided by the instance capacity, and then a magic number, which I really like. The ability to say, how long do I want it to take? So an example, we think we need about 150 tasks for a data set, so we're going to use an M1XL for testing, and it has 8 tasks configured. We select then 8 files, and we run a cluster, and we observe that it takes 3 minutes. We plug that into our formula, and we say, I want this to only take 5 minutes. Hey, presto, we need 11 M1 extra larges in order to process our data. And you can use that for any type of task that you're running now. And now you can have a great conversation with your business users. How long do you want it to take? Because keep in mind, and EMR makes this easier than almost any other platform today, that running 10 machines for 1 hour is exactly the same price as running 1 machine for 10 hours. So with EMR, you go wide. Go as wide as you can, and you get your processing done faster for exactly the same money. So we need to build transient cluster groups, and we encourage you to take more advantage of cluster resize than what we see customers doing today. All you have to do is change the instance count on any of those instance groups, and EMR will take responsibility for sizing up or down. And the processing of the cluster will continue while that resize is happening. So we might run a couple of core nodes, and we might expand those over time to increase our HDFS storage or to increase the amount of CPU and memory that we have access to. But we can't really practically remove them because HDFS replication will cause backups to be restored, and our HDFS system will become really busy, and it will stop processing useful data. So we add the task group, and this is where we see the greatest benefit for scaling your clusters over time. Add a task group which is not storing data, and then you can scale up as big as you want, keeping in mind that they'll be talking independently to S3 if you're using S3-based jobs, and then when you're done, get rid of them. The resize cases that we generally recommend you use are, for example, a smaller, always-on cluster, particularly when you have the need for ad hoc access by analysts. And then you expand that with task nodes during business hours. Keeps your costs low, keeps your customers happy. You can also add task nodes if you have variable workloads over time, whether that's throughout the day or seasonally. And we can also, particularly if we're shutting down our clusters, by adding task nodes which we place on the spot market, we can reduce the number of core nodes we require and thus pay less money. So when should you resize? Well, use CloudWatch. CloudWatch is provided free of charge with Elastic MapReduce, and it gives you details on things like the status of the cluster, the MapReduce, task and container performance, status of the node, I/O, HDFS, and HBase status. So the key monitors I would point out for you, the number of map tasks or containers that are running and remaining, and then, of course, the reduce equivalent. And then also look at S3 bytes read and written and HDFS utilization. Other thing you can do is just add nodes while your tasks remaining is non-zero. This will allow you to just go as wide as you need to, and then you stop when your forecast runtime is less than 60 minutes, because that's the point at which, yes, you're going faster, and you may have a business SLA to meet, so you keep adding nodes. But from a cost perspective, once your forecasted runtime hits 60 minutes, it's not going to save you any more money. So this is an example of a CloudWatch graph for a cluster that was running with a certain number of nodes, and then it was scaled up. And you can see that the number of map tasks running jumped to more than double, and then the map phase completed, and we see it just dropped off a cliff. So we doubled our processing capacity, very linear processing, and we look at the correlated status across this cluster, and we can see that the reduced tasks increased, the map and reduced tasks remaining significantly dropped, and we were able to go a lot faster. And these are all provided to you free of charge with the CloudWatch GUI, both for the EC2 instances that underlie your Elastic MapReduce cluster, as well as for EMR. So to sum up, and I appreciate your sticking around to the bitter end, we really do recommend that you take advantage of S3 as your system of record for durability and for ensuring that you have high-fidelity data. We really encourage you to save money and go a lot faster by practicing a cloud architecture applied to Hadoop using transient clusters, whether that's a small, always-on cluster, which you dynamically flex up and down, or completely shutting down your cluster periodically. And definitely use cluster resize to be able to make your customers more happy and then shed that load when it's no longer used. Please move to M3 and C3 to get better price performance, keeping in mind that if you're using heavy HDFS, you may still find that M1 and C1 offer you really good local storage capability. But generally, if your file system of record is S3, then you should definitely move to M3, C3. You'll go faster, and it'll cost you less. So with that, I would encourage you, please give us feedback on what you thought of the session. Certainly attend tomorrow's session on EMR data warehousing. And we thank you very much. We hope it's been useful. We'll be available at the front and at the QA speaker stands for any questions that you might have after fact. Thank you.